Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 8, Lesson 3, Quadratic Functions in Standard Form. In the previous lesson, we talked about vertex form and how that formula is helpful. Today we're going to look at a new formula that will also tell us key information about the function. In the Explore and Reason, we have these three functions graphed, and you can see they all have a leading coefficient of 2, so a equals 2. That means they're going to be the same width, right? The rate of change is the same for all of them. And we can see they're all upward facing. But what is different? Well, they have different vertex for each of them, a different vertex for each. And they do have the same y-intercept, so they're all crossing the y-axis at 0. What about the x-intercepts? So they have an x-intercept at 0, but then they each have their other x-intercept to the right. So we're counting by halves. So this is at positive 1, this one's at positive 2. This x-intercept is at positive 3. And if we're looking at the ratio of b and a, which is this linear coefficient over the quadratic coefficient. Remember, when we write standard form, this is a, this is b. So if we take b over a, what's the ratio of each of those? Okay, so for g of x, b over a, negative 2 over 2 equals negative 1. For h of x, the blue graph, b is negative 4 and a is 2, so that ratio is equal to negative 2. And for j of x, we have negative 6 for b. And for j of x, b is negative 6, a is 2, so that ratio is equal to negative 3. So the ratios of those two coefficients are different. Now compare that to their vertexes. Can you see something? So for a, the vertex is at 0.5 comma negative 0.5. So we're just looking at where the line of symmetry is. So for a, for the g of x, the line of symmetry is at 0.5. Okay, what's that relationship to our ratio of b over a? For h of x, our line of symmetry is at 1. So our line of symmetry is at 1 because our vertex is at 1 comma negative 2. And again, we're comparing the line of symmetry at x equals 1 to our ratio. What's that relationship? I'm looking for a pattern. And then for j of x, our line of symmetry is at 1.5, comma negative 4.5, well, that's where our vertex is, so our line of symmetry is at 1.5. What's the relationship between our line of symmetry and the ratio of b over a? Do you notice? Hopefully you're noticing that the line of symmetry is half of b over a. So remember that relationship. That's going to come back later in the lesson. So quadratic functions in vertex form tells us where the vertex is. But what information do we get from standard form? So standard form, just like standard form of a linear equation, I'm going to remind you really quick, ax plus by equals c, so we're going to have that constant, and then a is the coefficient in front of the first term and b is the coefficient in front of the second term. Okay, so that's a linear equation, just to show you really quick. Quadratic standard form, a is the coefficient in front of the quadratic term, b is the linear term coefficient, and c, of course, is the constant. We've seen this before when we were factoring our polynomials. So what information does c tell us? It's our constant. Well, hopefully you're recognizing it might tell us something important. So let's take a look. Here's an equation in standard form. C is negative 3. What else do we notice? Our y-intercept is at negative 3. For the second one, what do we notice? C equals negative 1. Where's our y-intercept? It's at negative 1. And for the third example, C equals positive 1. What's our y-intercept? It's positive 1. So our value of C in standard form is the y-intercept. That will tell us the y-intercept. Try it number 1. Evaluate standard form for x equals 0. How does f of 0 relate to the result in example 1? So if we plug in x equals 0 into our equation, what do we get? A times 0 squared plus b times 0 plus c. Well, anything times 0 is equal to 0, so those are going to cancel out. So then all we're left with is c. So when x is 0, our output is c, the constant. So this is the ordered pair for our y-intercept. Standard form of a quadratic equation, we already went over this, ax squared plus bx plus c, where a does not equal 0 because then that would get rid of the quadratic term. Okay. We know the y-intercept is c. There's another important feature that we can identify. So if we're looking for the axis of symmetry, remember it's going to be a vertical line, so the equation will be x equals some value. And to find the value of where that line of symmetry is, we're going to look at the ratio of b over a, just like we did in the warm-up. Except we notice that the line of symmetry, the x value in our ordered pair for the vertex, that was equal to half of the ratio of b over a. And so that's what we're going to do. The opposite of b over 2a, because that will be dividing by 2, this will tell us where the line of symmetry is. It gives you the x-coordinate also. So it'll give you the x-coordinate of the vertex. So if you remember this formula, opposite b over 2a, that'll give you your x-coordinate, whatever that number is, and then you can plug it into your function rule to get the y-coordinate. And that's what this says. Just plug in whatever value you get for the x and plug in whatever value you get for the x-coordinate, and then you will get the y-coordinate. And there is your vertex. So if you have an equation in standard form, you're going to want to remember this formula. Opposite b over 2a gives you x. It gives you the line of symmetry. It gives you the first coordinate for your vertex. Example 2, we can use that information to graph a function. So here let's identify what a, b, and c are. A equals 2, b equals 4, c equals 3. And then we're going to do our ratio to find the axis of symmetry. So opposite b over 2a, plug in those values. B is 4, a is 2. We simplify. So our axis of symmetry is going to be at -1. So there's our symmetrical line at x equals -1. And then we plug that value into our function rule. So now we're going to evaluate f of -1, plug that in. 2 times -1 squared plus 4 times -1 plus 3. We can evaluate that. And then we get our output, which is +1. So when x is -1, the output is +1. Here's our vertex. So we know two key pieces of information. Now we can graph it, just like we did in the previous lesson. Once we can graph the vertex, then we can pick other values for input and plot 2 other points and reflect them across the axis of symmetry. We also know the y-intercept is at 3, and then we can reflect that point across the line of symmetry. So we already have 2 points that we can graph right away, the vertex and the y-intercept. Then you just need to pick one other point, pick a small input value like 1 or -1, plug that into your function rule and get the output, and you'll have 3 points and their reflections to graph to make your good parabola. So that's what they've done here. They first graphed the vertex at -1, 1. Then they did the y-intercept at 0, 3. Here's the line of symmetry. So make sure you draw that as well so you can reflect over the line of symmetry. So after we've done that, we graph our second point across the line of symmetry. So notice it's 1 unit away from the line of symmetry. So we're going to move 1 point away from the axis of symmetry in the opposite direction. There's our reflected point. And then plug in x equals 1. We get an output. Here's our next point, 1, 9. And then reflect it. So that's 2 units away from the line of symmetry. So then in the opposite direction, go 2 units away. There's your reflected point. and then connect your dots with a nice curved line, and you have your parabola. Don't forget to put arrows on the end of your graph to show that it continues in both directions. Try it number 2, graph each function, and what are the y-intercepts, the axis of symmetry, and the vertex? Well, those are all 3 things that we need to be able to graph it anyway. So let's take a look at part A. Let's first identify the y-intercept. C is 4, so my y-intercept is 0, 4. Then let's find our axis of symmetry. X equals opposite b over 2a. Plug in my values. -2 over 2, which is -1. So I know I have a coordinate at -1 comma something. If I plug in -1 into my function, I can evaluate. So -1 squared plus 2 times -1 plus 4. When x is -1, my output is going to be 3. So my other point is -1, 3. Now I can graph that information. So let's graph our line of symmetry first. It's at -1. I like to use highlighters. You can use dotted lines if you don't have a highlighter. So there's my axis of symmetry. A good way to check is your vertex, remember, should be on the axis of symmetry. If I graph -1, +3, yep, it's on the axis of symmetry. So we did calculate that line of symmetry correctly. Now let's graph the y-intercept at 0, 4, and then reflect it over the line of symmetry. So there's 2 points. I need one more point to be able to tell how wide it goes. It's too close here to the vertex. So let's plug in +1. So when x is +1, 1 squared plus 2 plus 4, my point is going to be 1, 7. So there's my other point. Reflect it over the line of symmetry, and then we can graph our parabola, connect those with a nice curved line and arrows on the ends. Okay, part B, let's do the same thing. C is -4, so now I know my y-intercept is at 0, -4. Let's find the axis of symmetry. X equals opposite b, so -3 over 2 times -0.75. The x-coordinate is going to be 2, because -3 over -1.5 is +2. So I know my axis of symmetry is at +2. Draw it real quick. If I plug in 2 into my function rule to get the y-coordinate for my vertex, -0.75 times 2 squared is 4, plus 3 times 2 is 6, minus 4. And my y-coordinate is going to be -1. My output would be -1. So my vertex is going to be at 2, -1. I can plot that point. 2, -1. Does it lie on the axis of symmetry? Yes, it does. So we did that correctly. Let's now plot the y-intercept at 0, -4. 0, -4. And then reflect it. So I look like I'm having a downward facing parabola. Does that make sense? Yes, because our leading coefficient is negative. And let's do one more. Let's plot f of -1. So I'm going to squeeze it here. F of -1 to find a point out here. See how wide it goes. So -1 squared is +1. So this is just going to be -0.75. -1 times 3 is -3 minus 4. So I have -7.75. So my next point would be -1, -7.75. Can plot that. -1 almost to 8. And then we can reflect that. And there's our nice curved graph. Connect with a curved line and arrows on the end. Example 3. Our application problem, compare properties of quadratic functions. So thinking of how wide is the parabola, where's the vertex, where's the axis of symmetry, is it upward facing, is it downward facing, what's the average rate of change, which is related to how wide or narrow the parabola is. So we have this trajectory of the water from the fountain, so that's that curved motion again, making that parabola. from the fountain. And we have different fountains, different parabolas represented by an equation and a table. So this is the information we have for those two separate fountains, or those two separate streams coming from the fountain. So looking at the first one, fountain A, we know C is 8, okay? And we can figure out where the axis of symmetry is by doing opposite B over 2A. Okay, so we plug in the values. B is positive 2. 2 times negative 1. Notice there's an invisible negative 1 in front of the x squared. So if we calculate x, we get our line of symmetry at 1. And then we evaluate that. We plug that into our function rule to find the y-coordinate, or the output. So we plug in, remember, it's the opposite of whatever x is. So plug in 1 squared. The opposite of that is negative 1. Plus 2 times 1 plus 8, we get 9. So our vertex then is going to be at 1, 9. And if that's the vertex, that means the maximum height is going to be 9. 9 feet. Because that's the top. It's a downward-facing parabola. Let's look at the table for fountain B. What information do we have here? We don't have an equation, but can we find where the vertex is? Where does it change direction? So we can look at the outputs and notice we're increasing. So we're increasing 5, 8, 10, and then we suddenly turn around and go back. And it's symmetrical. It goes 5, 8, 10, and then goes in reverse order. So we know right here, here's our vertex. That's our turning point. And we know it's parabola because of that symmetry in the output, in the y values. So we know the vertex just by looking at the table. And since that's the vertex, we know the maximum height is 10. It gets 10 feet high. Try it number 3. We're going to compare this equation, or function rule for f. We have that function, and compare it to g. G is represented by the graph. So can we talk about maximum values, etc.? Why am I saying maximum? Well, I see in the graph that my parabola is downward facing. I can also see in my equation that I have a negative a value, so I know f of x is also going to be downward facing. So let's start with g, since we already have that. The maximum is at 0. The vertex is at 3, 0. We can just tell. How do we find the maximum, or the vertex, for f of x? Well, we're going to do the same thing we've done before. Find the line of symmetry, so x equals opposite b over 2a. Plug in the values. B is 0.6, negative 0.6. 2a is negative 0.3. And if I do the math, the opposite of positive 1 is negative 1. And then when I plug in negative 1, negative 0.3 times 1, or negative 1 squared, minus 0.6 times negative 1. So we're going to have to watch our signs. Okay, negative 0.3 times negative 1 squared becomes positive 1, so that stays. Negative 0.6 times negative 1 becomes positive 0.6 minus 0.2. So then I get 0.3 positive minus 0.2. So my output is 0.1. So my vertex is going to be at negative 1, 0.1. What's the maximum height for f of x? It goes up slightly more. The maximum is at 0.1. Example number 4, another application problem. We have that vertical motion again. She's throwing a ball up in the air, and then it reaches its peak and comes back down because of gravity. And here's the function for the height and the travel, the distance away from her that ball travels. So can we figure out the vertex form from that? So we can see that the equation's already given us vertex form. So from that we know we can write the vertex h, k, so h is 2, k is 8. So there's our vertex, and it makes sense because our a value is negative, so it's downward facing. That makes sense. So the maximum height it reaches is 8 feet above the ground, and it gets to its maximum height 2 feet away from where she threw it. So how can we turn vertex form into standard form? Because remember, standard form tells us other key information. It tells us the y-intercept. It'll tell us where it left her hand, like how high above the ground it was when it left her hand. So we want to have it in standard form. all we need to do is actually just do the math, just distribute. So x minus 2 squared, a squared minus 2ab. So 2 times x is 2x, double it is 4x, and b squared will be 4. All of that plus 8, and we're multiplying by 0.5. So then we're going to distribute the negative 0.5. We'll have negative 0.5x squared. Negative half of negative 4x is positive 2x. Negative half of positive 4 is negative 2 plus 8, and then we just need to combine our constants. So we'll have negative 0.5 x squared plus 2x plus 6. There's our standard form. So all we did was do the math. We just distribute. Make sure you square your parentheses first, and then multiply by the coefficient, and then combine your constants. So just remember your order of operations. Now, from our standard form, what do we know? The y-intercept is at 6. So the y-intercept is at 0, 6. That means when it leaves her hand, it is 6 feet above the ground. Try it number 4. Suppose the path of the ball in example 4 is this equation. So again, it's given to us in vertex form. We want to find the initial height, or the y-intercept, and we want to find the maximum height, or the vertex. So as it's written, we can already identify the vertex. So we know the maximum is going to be at opposite h. So it's already given to us. Opposite negative 1 is positive 1, comma k. So the maximum height, or the maximum, will be at 1, 6.25. So it reaches the maximum height at 6.25 feet. And then we need to do the math to turn it into standard form to find the y-intercept, or the initial value. So we're going to square our binomial first. So it becomes x squared minus 2x, so minus 2ab, plus b squared, which is 1. And then don't forget, we're also adding the 6.25. Then we're going to distribute distribute our coefficient, negative 0.25 x squared. Negative 0.25 times negative 2 is positive 0.5x. And then we have negative 0.25, and then we're going to add 6.25. So the last step, combine your constants, plus 0.5x. Make sure you're checking your signs. And then this is going to be positive 6. It makes sense. We should have a positive initial height. If we're throwing something, it can't be below the ground. So our y-intercept should be positive, so that makes sense. So the initial height is at 6 feet. Doesn't go very high, does it? We made it to the concept summary for standard form of a quadratic function. So remember, standard form can help you know the y-intercept, and you can identify the axis of symmetry using this formula. So you'll want to remember that, opposite b over 2a, and then you plug it in to find the y value for the vertex. You can use that to graph the function, and you can also turn vertex form into standard form to be able to get this information. If you have any questions, put it in the comments. Make sure to like and subscribe, and come back for lesson 4.